Alright, here's part 3 of 3 for this AB practice test. Here is a limit, but I hope that when you look at this that you recognize that this is the definition of the derivative. I believe that's in section 3.2 that we see this definition of the derivative, that f prime of x is equal to the limit as h approaches 0, f of x plus h minus f of x all over h. So what's the function here? The function is the easiest to spot right there. F of x is equal to sine of 2x, and you can see how this is the same thing with x plus h plugged into it. If f of x is that, and this is the definition of the derivative, well, we know what the derivative of that is. The derivative of this is cosine of 2x times the derivative of what's inside. It's 2. That's D. Uh, 22, we've got a slope field here. So I think the best way to do this is just to kind of check to see what works. So there's a lot of different ways you can approach this. One way is to look for zero slopes and see if they match up. So this is telling me that whatever the x-coordinate is, that when the y-coordinate is 0, I get a 0 slope. So I could just kind of pick a point here, like the point 1, 0, and try it in these and see if I get a slope of 0. That's the point 1, 0 right there. Do I get a slope of 0? No. So that is not a contender. Here, x at the point 1, 0, that would have to be a slope of 1, so nope. This works, and this works. Okay, so now I'm looking at the third power and the second power and thinking, okay, when I have a negative y value, I bet I should be able to tell. So let's look at these. When I'm at the point negative 1, 0, 0, negative 1, then does this give me the right slope? It looks like this has a slope of positive 1. So if I plug negative 1, the y-coordinate, into this, I would get a slope of negative 1, and that is wrong. If I plug negative 1 in here, I get a slope of positive 1, which is right. So by testing 2 points there, I was able to figure out which one is the right one. I don't think the right way to approach this is to try to make your own slope field from scratch and see if it looks like that. So that's how I would have suggested doing that one. 23, the base of a solid is the region in the first quadrant bounded by the y-axis, the x-axis, and the graph of y equals e to the x. Should know what that graph looks like. And the vertical line, x equals 1. So that's that region right here. And for this solid, each cross-section perpendicular to the x-axis, so we're slicing across it this way. We pull out one of those cross-sections. It's a square, and the side of the square is defined by the function, so the side of that is e to the x. What's the volume of the solid? This is in, I think, 7.2 notes, part 2, where we talked about how to do these volumes of with cross sections. So the area of this is equal to e to the x squared, which is the same as e to the 2x. And I'm integrating across the area. I'm not putting a pi on the outside because it's not a rotation thing. Its cross sections are squares. They don't have that as a wrong answer, but that's a possibility there. I'm slicing from 0 to 1, and the area of each slice is e to the 2x. Right. So the antiderivative of that is 1/2 e to the 2x. The 1/2 because you can either write out a u substitution, need a 2 in here, need a 1/2 on the outside, or because this is just like a linear factor of x, so you just have to divide by that. We've seen that enough that maybe you do that without writing out the u substitution. It's up to you. Up to you. 0 to 1. So I plug the 1 in there, and I get 1/2 e to the 2 minus 1/2 e to the 0. Just 1/2. So looks like going to be answer choice B. Number 24, graph of piecewise linear function. F is shown here. What's the value of this? I think it would be very tempting to like try to find that area, but the area, if you did that, this is the graph of F. That would be finding the integral or the area under this, and that is not what we're being asked to do. We're being asked to find this. So fundamental theorem of calculus says that the area or integral from 0 to 12 f prime of x dx is f of 12 minus f of 0. That is a basic statement of the fundamental theorem, which was in chapter 6, early chapter 6, if you need to review that. And f of 12 is -4, as this is just a graph of the f function, minus f of 0 is 4. That's -8. Number 25, this equation is a particular solution to which of the following differential equations? So sometimes we see these questions where we just have to kind of plug in the function and its derivatives and see which one that it agrees with. So let's just find y prime would be equal to 12e to the 6x, right? That's just a little bit of chain rule there, and the derivative of 5 is 0. The second derivative would be 72e to the 6x. Okay, so let's try some of these in these equations and see if they work. So for A, is it true that y prime, which is that, minus 6 times y, which is that, is equal to 0? Let's see, that's 12e to the 6x minus 12e to the 6x. That's true. Oh, I forgot the minus 30 there. Minus 30. And that would be minus 6 times that would be plus 30 minus 30. I think that checks out. That looks good. Let's just see that the other ones don't work so we can feel really confident about it. So 2 times y prime minus 12 times y plus 5 equals 0. This one looks okay for this part, the 24e to the 6x minus 24e to the 6x, but this, that's going to be plus 60 and then plus 5, so that doesn't work. The constant part of that is wrong. And then for C, the second derivative minus 5 times the first derivative minus 6 times the original equals 0. Let's see, so that's 72 of these, and then I got minus 60 and minus 12. So that part works, but then I don't have constants in either one of these, and I'm going to end up with a plus 30 there. So that can't work. This is our contender here, right? And then last check here, the second derivative, 72e to the 6x, minus 2 times the first derivative plus the original plus 5. So I don't think that's going to cut it here because that's 72 of these, and then I got minus 12 plus 2. That's not going to cancel out the 72. The 5s work out, but the other stuff does not. So We were right. It was the first one. Number 26. What's the value of x at which the minimum value of this occurs on the closed interval from 0 to 1? Looking for a minimum, so I'm going to go ahead and find the derivative of this. And that's y prime is equal to, multiply that out there, it's 4x to the 1/3, that's the power rule, minus 2. So I'm going to set that equal to 0. And so 4x to the 1/3 equals 2. So I'm going to let's see, I'm going to do that, and then I'm going to cube both sides. So 1/8 is a contender. So, but before we just jump in and pick that, I need to understand I'm looking for a minimum value on a closed interval. So the minimum could happen here, but it could happen at the endpoints also. So I need to test these and see what happens at those values. So when I plug 0 into this, I get 0. When I plug 1 into this, I get 1. And when I plug 1/8 into this, I get, let's see, 1/8 to the cube root of 1/8 is 1/2, and 1/2 to the 4th power is 1/16. And 3 times that is 3/16. And then minus 2 times 1/8 is would be that, right? I just got a common denominator there, so that's minus 1/8. So that actually is the minimum value. So it is in fact B. But checking the endpoints there is important because it could be one of those. At time t equals 0, a storage tank is empty and begins filling with water, and the depth of the water of the tank is increasing at a rate of this. So this is the rate. So integral of rate is equal to change in the amount of stuff. Right? That's the basic principle of that kind of thing. We did a lot with that in section, I think, 7.6. We did a bunch of practice AP problems, and that kind of thing came up a lot. Which of the following is the best interpretation of the statement that W prime of 2 is greater than 3? So this is already a rate. So W prime, that's the rate of change of the rate. So the rate of change of the rate at time 2 is greater than 3. That's basically what that says. So let's see what these say. Which one is saying some version of this? 2 hours after the tank begins filling with water, the depth of the water is increasing at a rate greater than 3. No, that's just saying, that's the same as saying that would be W of 2 is greater than 3. The depth of what, because this is the rate. Over the first 2 hours after the tank begins filling with water, the depth of the water is always increasing at a rate. No, it doesn't say, that's definitely not true, because this is just saying what's happening at 2, not like over the first 2 hours. For C, let's see what this says. 2 hours after the tank begins filling with water, the rate at which the depth of water is rising is increasing at a rate greater than 3 feet per hour. That looks good. And then D, over the first 2 hours of the tank filling, the rate at which the depth of water is rising is always increasing. No, it does. This doesn't tell us what's happening like for the first 2 hours. It just tells us right at that time. So, answer choice C. For 28, person stands 30 feet from a point P. That's feet. And watches a balloon rise vertically from the point shown in the figure above. The balloon's rising at a constant rate of 2 feet per second. What's the rate of change in radians per second of the angle theta at the instant when the balloon is 40 feet above from point P? Okay, so this is a related rates question, and related rates happened in section 3.7, in case you need to go back and review anything. So I need an equation. It definitely needs to have a theta in it. It needs to relate theta and other things in here by some formula from geometry. So if it's going to have theta in it, it's going to be a trig thing, right? So here's the theta, here's the height of the balloon, I'm calling that y, and here's this distance here. So we're looking at the tangent function. So tangent theta is equal to opposite over adjacent. And this 30, this distance from the person to point P, that distance is not changing. It's a constant. So you could, if you wanted to, move that over to the other side like this. Doesn't matter really. And then I'm going to take the derivative of this with respect to time. So 30, constant. The derivative of tangent is secant squared theta. And then in related rates, every time you take the derivative of any variable, a d, that letter dt pops out. Derivative of y, dy dt. So we want to know what is the rate of change. We're looking for d theta dt. Okay, so let's see if we can figure out the stuff that we need to know. So first of all, I'm going to do this. I'm going to solve for d theta dt. So on the other side of this equation, I'm going to have dy dt. The 30 is going to be on the bottom, so like 1/30th. And then when I divide by secant, remember secant is 1 over cosine, so if I move that to the other side, it just becomes cosine squared theta. And here, let's see what we can do here. dy dt is 2. It's rising 2 feet per second. There's my 1 over 30. And then the cosine of an angle, cosine is adjacent over hypotenuse. This is just a 3, 4, 5 right triangle, or a 30, 40, 50. So the cosine of this angle is adjacent over hypotenuse, 30 over 50, or 3/5 squared. All right, so that's a little, there's some stuff going on there to get to that point. Once we get there, we should be pretty good. Let's see what we can do. Let's try to simplify this as much as we can, get it to match up to one of these. So 2 over 30 is 1 over 15. 3 times 3, and 5 times 5 on the bottom. So here, one of those cancels here, leaving a 5. So 5 times 5 times 5, and then a 3 on the top. That is B. All right. How many vertical asymptotes does this graph have? Well, let's see. On the top I've got x minus 2. On the bottom, if I factor that, that's the difference of 2 squares. That's the same as x squared minus 4 times x squared plus 4. And then that's also the difference of 2 squares. So that's what the factored version of that looks like. Now there's an x minus 2 on the top, so x minus 2 and x minus 2, there's actually a hole at 2, not a vertical asymptote. That's back in Chapter 2, limit stuff. There is a vertical asymptote at x equals negative 2, and here this is always positive. X squared is going to be 0 at minimum, and then plus 4, so this does not cause any problems. So there is only one vertical asymptote. It would be at x equals negative 2. Last one. For what value of b does this integral equal that? That's crazy. Well, what this is a crazy summation notation version of a Riemann sum. And it's a little tricky to figure something like this out, but we are going to try to do it. We're going to pick a number n and then see what this looks like. So we're going to pick, let's just do n equals, I'm going to try to make it as simple as possible. I'm going to try to make it n is equal to 2, right? So that would be doing only 2 rectangles. And of course, this is letting the number of rectangles go to infinity, so it would actually equal that integral. So If n is 2, then I'm doing from k equals 1. I'm just going to make all of those n's equal to 2. So I'm going to have two rectangles here. The first one is going to be 1 plus k is going from 1 to 2. So this is where k equals 1. So that would be 1 plus 1 squared times 1. Right? This is like the height of the rectangle, and this is the width. When I plug in k equals 2, I get 1 plus 4 over 2 is 2. Times 1. Okay, and now I'm going to make a little sketch of this, of my x squared function. There's 1. So what do we have here? This is a rectangle that has a width of 1 and a height of 2 squared. Well, that's where, there's the 2 squared there, right? Because of the x squared function. And then here, sorry, that was my dog making that noise. Dexter, what are you doing? And this rectangle has a width of 1 and a height of 3 squared. So those are my two rectangles. So what's going on here? What we're approximating with this is it's a rectangular sum that goes from 1 to 3. So that's what we're looking at. That's a little tricky to figure out, but I think just picking a number and like seeing what you got is the best way to do it.